Okay, so we need to talk today about some advanced CNN architectures, which is very common, in fact, and we need to try it. We need to use, and you can train those models from scratch, and also maybe you can use it for transfer learning. In transfer learning, we have two choices. I mean, the CNN models anyway, they consist of two parts: one for feature extraction, and one part for decision making or classification, for example. So we can just import the part for feature extraction, because there are some similarities between different types of data sets, especially when we are working with images. And after that, we can build some new layers for classification. So today we need to talk about, some CNN design pattern. Pattern number one, it's feature extraction and the classification. We can use a whole neural network for feature extractions and the classification. And also we can use image depth increases and the dimension decreases. This is something also very nice. When we need to increase the depth of the image and decrease the dimension. And then better the number three, it's fully connected layers. We need also to understand some advanced architectures such as LeNet, AlexNet, VGGNet, Inception, and Residual Net. So this is something very common and very famous. People are using it in transfer learning. So it's very, very important to understand, those architectures. Maybe you can use it in your, we need to know all of them. We need to know the difference between all of them. It's a progress, and maybe they are started here. This one was invented, in fact, in 1998 until Residual Net, which is came in 2015 or 2014. So we need to talk about feature extraction and the classification, and in this case, the neural network, as we know, it will consist of two parts. One part called maybe I can. Yes. One part we call it feature extraction, and one part called classification. This one, it's convolutional layers, and those convolutional layers, they should extract some high-level features. So we have some raw images here. We will use it. We will stack some CNN layers together, and those layers will try to extract some high-level feature maps here. Those high-level feature maps will be used for classification. So usually we have those two blocks, one block for feature extraction, and one block consists of fully connected layers. We will use it for classification. And in transfer learning, because in transfer learning, maybe some models has been trained with images, and all images have something in common, right? So it should be theoretically correct that we use this one for feature extraction. We can import it from another model and try to apply it to our problem. But maybe our problem does not have the same structure here. So maybe they have been training AlexNet for classifying 1,000 images, objects, for example, and we need to use it for MNIST, where we have 10 classes. So in this case, I cannot use the fully connected layers, and we need to modify that part according to our problem. So this is then a classical approach, which we have been using a lot. We build one block for feature extraction, and after that, we have another block for classification. The block for classification, this is the shallow learning, which we know from before, right? We know this one very well. We have some fully connected layers. Those fully connected layers, maybe we have here activation function RALU, activation function RALU. Here, maybe the activation function will be softmax, because we need to classify into a number of classes. So you can import this one from any model and apply it to your own problem. But in your own problem, you need to modify that part according to the number of classes which you have. This one will be already trained, so don't need to train this one again. But this fully connected layers, it will be trained from scratch using our dataset. So if you are working with MNIST dataset, for example, I can import this one, for example, from LeNet, for example. But of course, the input volume here it should be, and we need to modify our new data set according to this one, maybe resize the image and so on. And after that, we will we will not retrain the weights here, right? We will not retrain the weights of the feature extraction block. And then when we, for the classification part, we need to train those layers from scratch, the weights here from scratch, using our small data set. So, so this is, I mean, what we are doing, for example, in transfer learning. So this one is composed of two parts, feature extraction part, which consists of a series of convolutional layers, and the classification part, which consists of a series of fully connected layers. So this is the classical structure. We have something else called image depth increases and dimensions decreases, right? So I mean, we will see we have an input volume, and this input volume has height, width, and depth. Correct. So this is for those layers. For those layers here, it will be, we will have, I mean, the feature map. It will has feature maps will have height, width, and not depth, but feature number of feature maps. Right? So maybe you are working with CFAR 10 or CFAR 100, for example. So the input volume here, it has height, width, and depth. So it's, I guess it's a 32 times 32 times 3. What about the feature maps? Maybe this one's a feature map. It will be, maybe the size will be 55 times 55 times 96. Correct? So it's 55 times 55 times 96. 96 here, it's not the depth of the image, but it is the number of feature maps, right? It will be the number of the feature maps. And the number of feature maps, it is something you need to decide by yourself. And we will do it also layer by layer. So maybe the next convolutional layers, I mean, the size will be, if we will use max pooling, so this one will be reduced into 27 times 27 times 256, for example. So the size of the image or the feature map, the size is decreasing and the depth is increasing, right? So so because we can go, I mean, in the last slide, for example, we can just keep all those numbers fixed, maybe just increasing the depth, right? But here, in each layer, we apply new convolutional layer over a new image. We apply convolution, and each image is a 3D object that has height, width, and depth. Depth is referred to as the color channels, number of color channels. If it is RGB, so the depth will be 3. The depth is 1 for grayscale images and 3 for color images. For example, in this data set, it was 28 times 28 times 1 because it's a grayscale. So it's a problem. If I need to use, for example, LeNet with MNIST data set, it will be a problem because LeNet was designed for, I mean, the input volume has depth equal 3 and MNIST has depth equal 1. So it will be a problem. Right?
By default, is equal 3?
It's by default, it's equal to 3. So if you want to use MNIST data set with it, it will not be possible. You need to convert it into, you need to extend the dimension, the third dimension into 3. Just copy it, the same. So just to have 3 copies in the input volume, because the filter here was designed for, I mean, it was designed for 3 channel. So in this case, you can just make it copies, or you can just try to find any function which can convert a grayscale image into RGB image, right? Maybe OpenCV or something, because black and white can be converted into RGB. So you need to convert it into RGB. You can just find a way to just make it 3 channels, not only 1, if you want to use a LeNet. So in later layers, the images still have depth, but they are not colors, they are feature maps. So we have here depth, but the depth here, it's not colors, because the depth here, it's RGB, right? Here it's 96. 96, it means 96 feature maps, right? 96 feature maps. In this pattern, the image depth increases and the dimension decreases, right? So we try to increase the depth and decrease the image size, height, and width. So you can just say it's a pattern of whatever, but it's so at the end here it will be 13 times 13 times 384. And if you want to connect it to fully connected layers, we need to flatten this one, right?
Yes.
So how can we flatten it? Just multiply, because this is a volume. So we just need to flatten it. So it will be 13 times 13 times 384. So it will be huge. It will be really. So maybe one way for reducing this one, you can use some dimensionality reduction layer, the one which you mentioned last time. This is very good. When you have the filter size 1 times 1, right? We use this one for dimensionality reduction to reduce the depth, number of the depth.
Yeah.
So for example, this one 13 times 13 times 384. Maybe you can use one layer with filter size 1 times 1. So in this case, I will convert from this depth number of filters into another number of filters. So I can convert this one from 384, for example, to 32. Correct?
Yes.
So in fact, this 1 times 1 filter, it do nothing, but it's just to try to reduce number of filters. And when we reduce the number of filters, when we flatten this one, instead of 13 times 13 times 384, it could be, for example, 13 times 13 times 32. So it's a big reduction. So it's a dimensionality reduction to try to avoid overfitting. Because we had this discussion last time, and it's a really very nice approach for. So we have also dimensionality reduction layer here. They call it reducer. Dimensionality reduction or reducer to reduce the depth of the image. So we can try to make fully connected layers much less capacity. So we try to avoid overfitting. So if we can say that this is pattern 2, we have also number 3, it's fully connected layers, we know it very well. So all fully connected layers in a network either have the same number of hidden units or decrease at each layer. It could be the same, but usually it's decreasing, right? So we go from 1024, maybe into 128 to 10. For example, if we are working with MNIST, 10 classes, or CFAR 10, for example, we have 10 classes. So you can go like this with the same number of units in each fully connected layers, but it's preferred to be like decreasing. Number of units should be decreasing a little bit. So it's rare to find a network where the number of units in the fully connected layers increases at each layer. I mean, it's usually, I'm teaching a similar course to bachelor students, and we're working only with shallow. And with shallow learning, I just try to say, okay, we need to have this like Billy, and I mean, it's like this one. So you start with small number, increase it, and decrease it one more time. So you can go also fix it, and you can go just decreasing. I mean, because if you will use if you will use dimensionality reduction, if we will use principal component analysis, for example, if we are working with images, right, and we will extract maybe 100 inputs from 28 times 28 pixels. If we will use the highest, maybe the first 50 principal components, so the size will be small. So in this case, maybe we need to just go wider, and after that go back again into. But I mean, there is no design structure for anything. It's by trial and error impact. So just need to try different combinations, architectures, and which one works with you. Yes. Now we need to study this LeNet. Maybe this is it was the first deep learning, first convolutional layers. In fact, it was 1998, and there's architecture composed of 5 weighted layers. It's called LeNet 5 because it has 5 convolutional layers, or 5 layers, 5 weighted layers. Those 5 weighted layers, it has 3 convolutional layers and 2 fully connected layers. So we have, for example, VGG 16. Why it's 16? Because it consists of 16 stacked layers. VGG 19. So this number usually is the number of layers. So LeNet 5, it's 5 because we have 5 layers. Those layers, 3 convolutional layers and 2 fully connected layers. This one, it's the first ever convolutional, neural network. And it was, it came to the world in 1998. And it used also hyperbolic tangent activation function as an activation function instead of, the state of the art, for example, ReLU, because at that time, ReLU has not been used in deep learning. So in this neural network, in fact, they used hyperbolic tangent as an activation function. They didn't use sigmoid because sigmoid, the output will be I mean, it squashes the input into 0 and 1. So it's not symmetric. All inputs are squashed into a value between 0 and 1. But in hyperbolic tangent, all inputs are squashed between -1 and 1. So they feel it's symmetric. So when it's symmetric, the conversion speed will be much better. Convergence speed will be much better. So this one, I mean, imagine that we have an input. The input is MNIST image, it's 28 times 28. So the first layer, I mean, the first layer is a feature maps. It will be 28 times 28 times 6. So just selected 6 feature maps. So the depth here will increases from 1 into 6, right? And after that, we will have subsampling, or how can we do subsampling? How do we use subsampling? Using max Boolean or average Boolean, correct? So we will do this subsampling. So this one will convert it from 28 times 28 into 14 times 14, the same number of features, 6. So I mean, subsampling here, it means we are using Boolean layer. So we have the first convolutional layer, and followed by Boolean. It could be max Boolean or average Boolean. Yeah, it's
Maybe
average.
padding.
Huh?
Maybe padding.
Padding?
Padding, yes.
No, you use padding. Maybe you are using padding here to keep the same size, right? So are using padding
When you
here?
use, for example, valid one, you can decrease the dimension.
Oh, no, but this one, it's the same dimension, which means it's the same.
No, for the third line, yes. Maybe before that we use the padding.
But even if you will use it, how this one will reduce from 28 to 14?
Yes, it's possible. With valid one.
Okay.
We have two types of padding, same and valid.
Mm-hmm.
When we use the same, the output will be the same size of input.
Mm-hmm.
But when we use valid, we can reduce the dimension.
Okay, so this one is 2 times 2. So the average Boolean here is 2.
Maybe, I just guess.
Mhm.
Yeah.
No, it's the stride equal 2, and the filter size is 2 times 2.
Yeah.
And when we apply 2 times 2 to the 28 times 28, we will get this one to the half.
Yeah.
It will be 14 times 14.
Yeah.
So we use average padding. And average padding, we will just scan 4 values each time, because the filter size is 2 times 2, and we will calculate the average, and we will, so in this case, we will subsample this one into this one. So after that, we will apply another convolutional layer, and in this convolutional layer, the filter kernel size, it will be 5 times 2, 5 times 5, with the stride equal 1. So we will get 10 times it. Maybe here we use the valid padding, correct? Because the dimension decreased, correct? Into 10 times 10, from 14 into 10 times 10, which means we didn't use here padding, 0 padding, correct?
Yes.
So it's valid.
Yeah.
Mm-hmm. So now the dimension has decreased to 10 times 10. We selected 16 feature maps, right? We selected 16 feature maps. After that, we will use subsampling. This subsampling also, we will use average Boolean. The same average Boolean, the size will be 2 times 2, and the stride equal to 2. So we will get those 16 feature maps of size 5 times 5. After that, we will just flatten it, correct? And we will have 2 fully connected layers. This one flatten, correct? When we flatten, we will get, it's 5 times 525. How can we get those? He said it's two fully connected layers, right? Okay. What is C5? Okay, this is fully connected Gaussian. I don't know. Maybe this one, it's fully connected layer, it's 120. This one, 84. Maybe this one for, they call it Gaussian connection. I don't know. Maybe they call this one fully connected, this one fully connected, this one for just a classification using a Gaussian. Because when we flatten this one, it will be 5 times 5 times 16. So how many 5 times 25 times 16? So how many values?
More than 300.
300. So
More than 300.
so we will flatten it. We will get those maybe 300s. Maybe this is the first fully connected layers. Why is it called it C5? F6. Maybe this is fully connected layer. This is convolution. What does it mean? So we have 3 convolution. So this is the first convolution. The second convolution is the third convolution. So they will apply again convolution here, and they will get 128 values. I don't know what kind of, it's applying, maybe applying 5 times 5 times. Okay, so we will apply here the first convolution, we will get this one. Average pooling, convolution, average pooling. We will apply again convolution here, by the way. So in fact, really, we have two fully connected layers.
Oh, you got 120?
By applying, by maybe this is 5 times 5 times 16. If you will apply another convolution, maybe using 5 times 5 stripe equal 1, maybe, I don't know, which size you will get here. If it's, if you will use, maybe you will not use padding here.
Here, for example, 5 times 5. So,
3 times,
four filters with the size of 4, 5 times 5.
yes. So maybe we need to dig more into, I mean, the structure to find what is the size here, what is the filter size here, and number of feature maps to get 120. So in fact, I used this one for.
Sorry, Ibrahim, I have just a question about this type of transfer learning models. We can just transfer the learned weights to the another model, just weights?
Yes, yes, the weights. So first you need to define a model called LeNet. You can just define, you know the structure now. You can build it from scratch, layer by layer. So you can define a sequential model, and you can add those, because now we know the layers. We have how many layers we have? We have 3 convolutional layers. We know how much padding, how much, we know all those hyperparameters. So you can build the model from scratch, one layer after one layer.
Yeah, I know, just...
and retrain the model.
Okay.
If you will build a model from scratch, you cannot, you can import weights as well also. So,
yeah.
But you need to follow the same structure. You will get an error message if there is something different. So in transfer learning, I mean, you can build the model layer by layer, right? Because we know the structure, but we need to be careful to build it exactly the same as the one which they, I mean, trained, for example. And after that, you can just upload the weights to the model. But if there is something different, for example, if stride is different in one, filter size is different or something, you will get an error message. Or you can import the model as one layer, the whole model as one layer in your model.
I know about that. Just, for example, we transfer the learned weights to the another model.
Yes, another model?
Yeah, yes, because that is the...
A different model?
Yes,
no, it will not be possible.
Not a different model. For a different, the same structure.
The same structure, it's fine.
Yeah.
So you can just import this one as one line.
Yeah.
Or you can build it one layer by one layer.
Yeah, I know about that.
Yes. And the import, you need to load all those weights. It will be okay. But if you will build your model from scratch one layer by one layer, you need to be careful that you are using exactly the same numbers. Exactly the same numbers. Otherwise, you will get an error message. Right? But for simplicity, you can just import the model as one layer. But if you will build the model from scratch, maybe you can build the same model and retrain the model. Because now we know that we have the data set. We have better GPUs. I mean, they trained it in 1998. It was very complex at that time. Now it's much better, right? Maybe also here they used hyperbolic tangent. You can just rebuild the model. And instead of using hyperbolic tangent, you can use ReLU. Correct?
Yeah. And for example, if you have a new problem with the different layers, for example, the first layer, second layer, and third layer, we can use for each layer different transfer learning models.
For each layer?
Yes.
Import it?
Yeah.
Yes, of course. I mean, you can build, I mean, because I can import this one as one line, and I can just maybe use some of those layers and, right?
Yeah. Okay.
So I mean, for example, you can import this model, and you can say, okay, I will retrain the last layer, because the last layer is the one which is closer to the fully connected.
Most important one.
So this is the most important one, because this one will help us to extract the, I mean, most important higher level feature maps. So you can just say, okay, I will train this one.
Yeah.
So you can import the model, all model parameters, all model weights, right? And disable training those layers, and just to train this one. with the fully connected layers. So they call it fine tuning, right?
Yeah.
Because I can import this one and tune only the newly fully connected layers which we added. In this case, we call it full transfer learning, for example, or you can disable. You can train some layers here. Maybe usually it's the layers which are closer to the fully connected layers. Maybe I can just train the last convolutional layer, right?
Yes.
So in this one, I will train this one with the fully connected layers, and they call it fine tuning. I fine tune my transferred model. I will not just use it as it is, but I will fine tune its weights using the data set which we have.
Yeah.
But we need to be sure that we have enough data for training it. So if you can go to this code, LeanIt 5 MNest, I just so in fact I have been testing it with MNest, right? So this is the model. So this is the model, okay. I just built it from scratch. I guess we have convolution, average pooling, convolution, average pooling, convolution, flatten, and the two dense layers, right? Two dense layers. So in fact here, the input volume was 28 times 28 times 1. Now, it's 28 times 28 times 6. Number of parameters here, it's 5 times 5 times 5 times 5. Can you divide 156 by, it's 5 times 5 times how many? 6? 6 feature maps? Yes, 6 feature maps, yes.
Yeah.
So in fact, it's 5 times 6 plus 6. Can you check it? Correct? 5 times 5 times 6 plus 6 should be 156.
156.
Yes. And after that, we will apply average pooling. So we will get this volume. The second convolutional layer, we will apply 5 times 5 times 16 plus 16.
Yeah.
Correct? We will get this volume. So this number here, it should be 5 times 5 times 16 plus 16. After that, we'll apply average pooling. We will get this volume, and after that, we got 120. Yes, this is 120. So it's maybe it's 5. Can you multiply, please? 5 times 5 times 120. Can you multiply it? 5 times 5 times 120 plus 120. And here, we didn't use here max pooling, right? We didn't use average pooling. No, oh, sorry, we applied this one. No, we didn't use padding. We didn't use zero padding. Hello, Mingita? We didn't use padding, right? So the volume here decreased from 5 to 1, right? The volume decreased from 5 to 1. How many? 5 times 5 times 120 plus 120.
3,120.
Huh?
3,120.
Okay, so we have a problem here. So how can we get this number? How can we get this number? 5 times. Okay, it's multiplied by 16. Sorry, multiplied by 16. So it's 5 times 5. This is the filter size. We will multiply it by 16, multiply it by 120 plus 120. 48120. Right? So this is a number of parameters here. So if we need to give this number of parameters, because the filter will be applied to 16 channels, or depth will be 16. So it's a 5 times 5 times 16 times 120 plus 120. So finally, we have 120 times 1 times 1, which is 120. So when you flatten it, we will get those 120. So now understand from where we got 120. After that, we will use two dense layers. Number of units here will be 84. Number of units here will be 10. So we can use this one for training MNest data set. So this is The accuracy is 98.7%. This is the training and validation loss. And this is the training and validation accuracy. And also this is the confusion matrix. Should we go to the code? Do you want to go to the code? Do you want to go to the code?
If you like.
Yeah, sure.
Okay. So I will share the code. Okay. Okay, so I mean, this part, no problem. I mean, we know this part. We just load data mnest. So keras.datasets.mnest. We loaded our data set. And of course, we need to categorical. We need this function because we need to convert, labels into one hot encoding. We import a model as a sequential. We import layers, conv 2D, average, pooling, flatten, dense. So this is our data set. Our data set, it's fine. We didn't make anything because our data set it's 28 times 28 times 1, which is okay for our model. And after that, we need to, in fact, we don't need even, we don't need to, normalize it, but it's okay because in this model we didn't use RELU, in fact. We used hyperbolic tangent function. So this is the model, LeNet. So this is the model. So as I told you, you can import the model as one layer in your model and disable the fully connected layers, right? Or you can just build your model from scratch. So if we need to build the model from scratch, we have the first convolutional layers. We need to get 6 filters, right? And the size of the filter will be 5, or 5 times 5. Stride equal 1. Activation is hyperbolic tangent. The input shade is 28 times 28 times 1, and padding is same, right? We will use padding in the first convolutional layer. After that, the second layer will be average pooling. So the pool size will be 2, stride equal 2, padding is valid. Padding is valid means we don't have padding, right?
0 padding.
Yeah, what?
0 padding.
It's called 0 padding because 0 padding means we add 0 rows and a column. So it's called 0 padding, right? Yeah. But we have 2 options. We can add it or we cannot add it, right? So if you will use 0 padding, we call it same. If you will not use 0 padding in Keras, if you will not use 0 padding, we need to call this one valid. But it's a 0 padding. Maybe someone else can just say, okay, I will add a pixel of 1, not 0. We can call it 1 padding, right? So 0 padding means we add padding with pixel value equal 0, right? So now we have padding equal same. So here it's valid. As a second convolutional layer, we need to get 16 feature maps. The size will be 5 times 5, stride equal 1. The activation also, it's hyperbolic tangent. As I told you, at that time, they don't have RELU, 1998. So they don't have RELU. After that, it will be followed by average pooling. Pool size will be 2, stride equal 2. We will add the third convolutional layers. Number of filters will be 120. The kernel size will be 5, right? But when we apply this one to this one, at the end, it will be 120 times 1 times 1, right? So we'll have 120 values. The last convolutional layer, number of filters is 120. We need to get 5 times 5. Stride equal 1. Activation also, it's hyperbolic tangent. We will flatten it, and it will be followed by 2 dense layer. Number of units in the first dense layer will be 84. The last one, it will be 10. The activation function here, it will be hyperbolic tangent. Here, it will be softmax. Why softmax? Because we are classifying, we have 10 classes. So this is the model. We will not import the weights. We will train it from scratch. We are not importing the weights from somewhere, but we will train it using our MNIST data set. So this is how the model looks like. And I mean, we use SGD as an optimizer in categorical cross entropy, and we just train the model, right? So the accuracy, I mean, we started already with very good accuracy. Means the validation accuracy was 91%. And after 20 iterations, 98.7%, which is really very, very good, right? Shows us just plotting those graphs and plotting the confusion matrix. Mhm. Yes. So this is LeanIt. Any question in this one? So here it's the structure, which is common structure, or I mean pattern, which is famous one, LeanIt, and you can just apply it to your data sets because they have been experimenting with this until they reach this configuration. It was 1998. So now you can just modify this one, for example, use different activation function. Here, I mean, we have to, in fact, normalize our data. We are not normalizing at the moment. So if you are using activation function ReLU, for example, we don't need to normalize this one, but we normalized it because we are using hyperbolic tangent. Right? Hyperbolic tangent, it's the output will be a number between -1 and 1. So it's very, very important to normalize this one. Why hyperbolic tangent? Why not sigmoid? Because the sigmoid, the output will be number between 0 and 1, right? So this one is hyperbolic tangent to be like this one, but sigmoid to be like this one.
Between 0 and 1.
Yes, the output here will be between 0 and 1, but the output here is between -1 and 1, because they feel when it's a symmetric, I mean the model will converge faster. Yes. Any questions? Any questions?
LeanIt is good for pictures with 3 channels. Yes.
This one?
LeanIt. Doesn't matter, yeah?
Maybe. Right. It could be. But I mean, they did it. In fact, it was competition for MNIST data sets, and they were maybe the first winner. That is, they can reach a very, very high accuracy at that time, in 1998. But if you want to apply it for 3D imaging, you have no problem. Why not? Right? You just need to try. And so, for example, try this one with CFAR10, because CFAR10 it's RGB image, right? Yes, I mean the second one, in fact, it's AlexNet, and AlexNet, it's a very famous one. You can in computer vision, and it's presented in 2012, and it's a series of convolutional and pooling layers stocked on top of each other, followed by fully connected layers and a softmax. So this is a traditional structure which we are using today, correct? This AlexNet. So in fact, a number of convolutional layers stacked together, and on top of it we have those 3 fully connected layers. And we have an input volume, and this input volume, it's a depth of 3, so it's RGB image, and first convolution followed by some max pooling, convolution followed by some max pooling, and so on until we have. So it's five convolutional layers followed by 3 fully connected layers. So in fact, in total, it consists of 8 layers. And it's similar to LNet, but it's much deeper. So I mean, the other one, it was 5 layers. Here, this one, it's 8 layers in total. So it's just much deeper and bigger. So it has more filters, more filters per layer. So it's deeper and bigger, right? Deeper because it has more convolutional layers, more layers, and bigger because we try to get more, I mean the depth, bigger in terms of the depth of the feature maps. So now we have 96, 256, 384, right? And so on. So the input volume, it's RGB image, and we use here, I mean the filter size here, it's 11 times 11. We use a stride of 4. We will get this volume, and after that we will apply 5 times 5 filters. We will get 256 feature maps, and so on. So AlexNet has about 60 million parameters and 650,000 neurons, which gives it a larger learning capacity to understand the more complex features. So this one has more capacity, in fact. Now we understand what is model capacity. So model capacity, it's number of parameters and number of neurons in your model. So when your model has higher capacity, It means it can handle more complex data sets. And it has been trained using ImageNet. The ImageNet, it's a visual database designed for use in visual object recognition. And it has today more than 14 million images categorized into almost 22,000 categories. So it's a very huge data set, right? So this one has been trained using ImageNet. So today, for example, if you are working in image recognition, for example, I mean, there is no need, in fact, to start from scratch, because you can just use AlexNet, for example, and try to change those dense layers according to your problem. Retrain those fully connected layers, your limited data sets, and just use this this model for. We don't need to start from scratch. If we have something which is really working very well, so we don't need to start from scratch. So this is AlexNet in more details. We have this input volume. So the input volume should be 227 times 227. It has been trained using this one. But when we need to deploy it today, we don't need, in fact, to stick to this one. There will be some minimum size. Maybe the minimum size will be 75 times 75. How can you define this minimum size? It's based on the volume and bedding and stuff like this. So when you check the documentations of each model, you will get, this is very important to know the minimum size. What is the minimum size? Do we need to resize our data set to be the same size or not? No, we don't need to stick to the same size. It could be smaller than this one, right? So the input volume was 227 times 227 times 3. We apply this 11 times 11 filter. So we need to extract 96 feature maps. Stride equal 4. When stride equal 4, so the output volume will be 227 minus 11 divided by 4 plus 1. So it will be 55, right? It will be 55. So the feature maps, it's 55 times 55 times 96. So we get 96 feature maps. After that, you will apply max pooling of 3 times 3 filter size stride equal 2. So we will get 27 times 27 times 96. You will apply another convolutional layer, 5 times 5 bedding equal. Those numbers are very complex, by the way. And then when they have been building those models, they've been experimenting a lot. Because which filter size, which will give us better results and so on. So they've been testing a lot, in fact, until they come out with this, nice structure, for example. So at the end, we will flatten, and then when we flatten here, we will add some fully connected layers. But I have been searching a lot. Did you use this AlexNet in Keras or something? No. Because I have been searching a lot, but because it's very manual, in fact. You need to get a file with weights. You need to build your model and upload your weights from a file. It's not like VGG16, for example. You can get it from Keras.applications, but we need to do this one very manual, in fact. So if someone of you has been working and trying with this one, it's not in Keras.applications. So it's not very easy to work with. You need to build the model from scratch as this one, and you need to upload the file. So transfer learning, example of applying a transfer learning, for example, to VGG16, for example, we freeze the feature extraction. The model consists of feature extraction part and the classification part. So we need to freeze the feature extraction part of the network and remove the classifier. We don't need to the classifier. Because, for example, AlexNet has been trained for classifying 1,000 objects. Maybe in my application, we are not interested in 1,000 objects. We need to classify to 10 or 100, for example. Could be CFAR 100, for example. So in this case, I need to remove the classifier, and I need to freeze the feature extraction part. I don't need to retrain that part. So we need to freeze it, right? And remove the classification part or the classifier, and add our new classifier add our new classifier, and the pre-trained network is used as a classifier. It could be also used as a classifier or as a feature extraction when the target domain is somewhat similar to the source domain. So it's very, very important. If I want to transfer learning a model, for example, I need to be sure that it has been trained using a similar data set to the data set which we are working with. Otherwise, it will not, I mean, help you. So it's a very, of course, there are some common features between different data sets in images, for example, but it's a very important. So if you are classifying something at night time and you are using a data set which has been trained using daytime images, it will be a problem, right? So when we transfer learning, we need to be sure that there are something in common with, between the different types of data sets which we are using. So
But maybe we will have new features in the new data sets, which we are trying to adopt a network for that data set. So maybe we have to train a little bit.
Yes. So in this case, maybe we need to retrain part of the feature extraction model. So maybe, for example, in AlexNet, we have five convolutional layers. So you can just retrain the last convolutional layer, the one which is in charge of extracting the high-level features, right? So if you want, this is very good. So they call it fine-tuning or something. So for example, here, maybe this is hard to retrain that part, but maybe you can just go for this last convolutional layer, right? Because this convolutional layer, it's the one which is in charge of extracting those high-level features. And I need to modify those high-level features. So in this case, I can just train only this layer, not the whole. So instead of freezing the whole feature extraction part, I can just freeze it and allow for retraining the weights of this layer, for example. So in this case, I can just modify it in a way to help me to solve my problem. So don't need to freeze, maybe you don't need to freeze the whole model, feature extraction part. I can just maybe select one or two layers and retrain those layers. Because we need to modify those, high-level features. Yes. So this is an example of AlexNet, for example. So this is AlexNet model. This is the full model. So we need to freeze the weights in the feature extraction. We need to freeze that part, and we need to remove the classifier, and we need to add maybe softmax layers or a different classifier. So we need to add something different here for classification. So we can just remove the classifier, which is fully connected layers, and add a new classifier to your model. We will freeze that part, and we will train only the weights of the fully connected layers, right? But as you mentioned, Hamad, maybe you can just select one of those layers.
But in this case, I guess we are just reducing the number of classes in the softmax layer.
Number
we are
of?
not transfer any learning in this case, I guess.
You can what?
In this case, I feel like in the softmax layer, we are just reducing the units or number of classes which we have to classify. But in this, we are not transferring any knowledge.
No, we transfer the knowledge from the feature extraction part. This one, because if we are extracting some features, there are some common features. We are working in images and stuff like this, and there are something in common, in fact, between all images. There are something in common. And this is the idea behind using transfer learning. So instead of retraining this complex model using a data set which we have, which might not be enough, because at the end here, we need to extract some high-level features. Those high-level features will be, we will provide those high-level features to the fully connected layers for classification task, right? So we assume that there's something in common, right? And we will use the same high-level features for our problem. But maybe here, for example, maybe if you develop this one for 2 classes, and my problem has 10, so I need to change this one into 10, correct? And if you will change this one, so you can just say, okay, I will go for 2 fully connected layers, or 3 or 4, it's as you want. And also you need to design, what will be the structure of the fully connected layers. And then now we are initializing those weights from random values. So we need to retrain that part. So we need to freeze that part, right? And we will provide all our images here. So when we put a new image here, we will get some high-level features here. Those high-level features, it will apply to the fully connected layers, and we have some decisions, and we will calculate some error here, and we will use error back propagation to adjust weights back. We will adjust only the weights here. We will not touch that part. So this one will be used as a buffer, right? So it's a transfer learning because we don't need to retrain the part one more time. We will just use it as it is, right? If you are sure that it will be very helpful for you. But as you mentioned, some people, they just can train some convolutional layers here, especially the last one, because the last one, it's the one which will be in charge of, because we need to modify those feature maps. I don't need to use exactly the same feature maps from the original system, but I need to modify them a little bit. So in this case, I can try also to retrain the last two convolutional layers to change the feature maps, because maybe there is something different. So maybe if the performance is not very good, you can just train this one also as well. So they call it in fact fine tuning. So if you are freezing the convolutional layers only, then you are using the pre-trained network as a feature extractor and transferring all of its high-level feature maps to your domain, right? So this is, we call it transfer learning. So if we use the feature extractor part as it is, we will not touch it. So we will just use it for generating those high-level feature maps, and we will just add some fully connected layers for classification or for decision making, right? So the formal definition of fine-tuning is freezing a few of the network layers that are used for feature extraction and jointly training both the non-frozen layers and the newly added classifier layers of the pre-trained model. So in this case, we will not freeze all layers of the feature extraction part, and we will allow for retraining some layers. It is called fine-tuning because when we retrain the feature extraction layer, we fine-tune the higher order feature representations to make them more relevant for the new task which we have. So you don't need to freeze the whole model, but you can just decide, okay, because I mean, we have an input volume here, we will get feature map 1, 2, 3, 4, and after we will flatten, we will have a classifier. The classifier is new, is brand new, right? Now we need to use this feature extraction part. So you can just try, okay, I will try feature map 4, right? If the accuracy is still very low, so in this case you can say, okay, now I will not freeze the whole model, I will freeze those 3 layers and I will just retrain this one. When you retrain this one, in fact, we will try to modify the feature map number 3 into something customized to my program, right? So you fine tune it. So you can try, okay, if I will stop here, for example, so I will train this one with my classifier. I can stop here, I can train those with my classifier, and so on, right? So in this case, you try to fine tune, you try to make good mix, in fact, between the feature extraction and your classifier. We make some integration. So instead of importing this one fully, because maybe the generated feature maps here, it will not be very relevant for my problem, right? Because the load will be very high for the classifier, in fact, to adjust, to try to find some weights and combinations to make decisions, good decisions for us. Maybe it will be very tough for the classifier. So in this case, you can just say, okay, I will retrain the last convolutional layer to modify those feature maps and to get something really very relevant for the problem which we are.
Can't we add more
No,
convolution layer?
we don't add. If you want to add, it's up to you as well. I mean, but we don't add. Usually, it's not adding, but you just select. I mean, you can just go for the last convolution layer. Don't freeze it. You freeze the model anyway, but you can just allow for. You don't freeze all layers, right? You just select. Maybe this one will be frozen. This one will be trained with the fully connected layers, right? And it could be also a good idea to add another convolutional layer. So the input to this convolution. So if you want to add a new convolutional layer here in the middle, so the input to it will be those feature maps, and you will get different feature maps. If you will train this convolutional layer, maybe you will get something. So I mean, there is no rule for anything. It's just a trial and error, in fact. But you just need to know that there is a difference between transfer learning and fine tuning. When it's fine tuning, we will not freeze all layers. We will retrain some of the convolutional layers with the fully connected part.
Maybe we can retrain any layer in the middle.
One in the middle.
From the middle.
Yeah, but it's a logic.
Based on the like visualization of feature maps. Because at each layer we can, I guess, visualize what type of like activation is happening.
It could be, but it's more logic that we need to start from the back end here, right? The one which is connected to the classifier. Because you have a feature map here, maybe this feature map is not relevant at all for my problem, so I need to modify it in fact. So when we retrain the last convolutional layer, we try to modify those high-level feature maps into a new feature map which is more relevant to my problem in fact. So because it's data-driven, so now we allow for adjusting those feature maps and connect it to the data which we have. Because this one has been trained in different data sets, we are getting here some standard feature maps. Maybe those feature maps are not very relevant to my problem. So in this case, we try to make some changes. Because people complain from those Bausa. Should we take a break? Okay, we will take this slide and after that we will take coffee, right? So this is an example. We have data sets and we try to extract, this is what we can see in fact. You have some input volumes. From those input volumes, you will get some feature maps, and this is high-level feature maps. Maybe this one it's relevant. This is faces, this is cars, this is elephants, chairs. Do you see any similarity? Maybe they are the same. So maybe if I train the model for faces, I can use the same model for cars. If I train the model for cars, maybe I can use it for elephants and the chairs, right? If it is okay, it's fine. So in this case, you will fully transfer your feature extraction part as it is. But if it's not working with you and the accuracy is low in some classes, for example, so in this case, we need to fine tune some convolutional layers. We will freeze the whole model, but not the whole model, some layers. We will freeze some layers, and we will allow some layers to retrain using the data set which we have. In this case, to improve the performance of your model. But it's challenging because you need data, right? If you will train a convolutional layer, you need some data, but maybe the last one, why is the last one? In fact, because the last one also the dimension of the feature map is smaller, right? So it's not very complex compared to the input volume, right? Maybe the input volume it's 227 times 227, but the last one, maybe the last layer, it's 1 times 1 times 120, maybe. So it's something which is easy to customize. Maybe it's 3 times 3 times 120. So the size of the image or the feature map, the dimension of the feature map, it's much smaller. And in this case, we need less data, in fact. Maybe the data which we have would be enough for fine-tuning the last convolutional layers to get some higher-level feature maps which are more relevant to the data, to the problem which we are solving. So it's a trial and error. You need to try it by yourself, right? And yes, so we will take a break now, and we will start again after 10 minutes or 15 minutes. So please just bring your coffee, and if you have any questions online, just please ask your questions. And we have coffee here. Do we have coffee ready? Or?